Hello, Nick Leifker here, and welcome to Management 409, Operations Management. We've talked about this need, this desire to balance the process. Well, there's a reason for this. There are reasons why we need to balance the process, why we want each part of the process to have as close a throughput rate as possible, to have, if you will, about as much work as possible. Because what we ultimately want to do is we want to increase the utilization of the process. Now, we need to be a little careful about this, and there are reasons for which I'll explain later. But what we want is we want people, while they're working here, to actually be working. We don't want people sitting around doing nothing and not have any work available. So we want to increase utilization. And what utilization is it's a ratio. It's, in many ways, a measure of the percentage of time that a step is actually in use. So it's, if you will, the percentage of the capacity of this particular step that is actually in use. So utilization is simply the actual throughput rate over the design throughput rate. Well, what are those? Well, the actual throughput rate is how fast it's actually going. So, it's pretty much what it says. The design throughput rate is how fast a step in the process could go if it wasn't being blocked or starved by anything. In other words, if this step in the process could go as fast as it absolutely possibly could without having to worry about anything that any other step in the process or any supply or any demand going on. So it's how fast this step could go if nothing else was interfering. So utilization is this actual throughput rate over designed throughput rate. Now, when it comes to utilization, we want a utilization that is good, somewhere around 0.8 would be nice, but it's dangerous to have a utilization close to 1. And the reason for this is that what tends to happen when we get a utilization close to 1 is the process becomes so bogged down that due to uncertainty, due to variation, we end up not being able to get anything done. It takes an infinite amount of time, if you will, for an item to get through the process. So we don't want a utilization of 1, but we do want a fairly high utilization, 0.7, 0.8, somewhere around there. That would be nice. So while people are working, while people are there, we want them working. We want them productive. We want them getting stuff done. Now, I'm not going to go into the math details as to why utilization of exactly 1 would be bad. But suffice it to say that, well, have you ever seen a traffic jam? A traffic jam is a utilization of 1 in a case where there is uncertainty, where there is variation in the process. Now, we'll talk a little bit later in this chapter about why uncertainty is bad for a process, and that's pretty much why. What ends up happening is, because you can't get time back, if you have utilization that's so close to 1 for your process, then it can actually bog down. It can take too long for people to go through the process. But we do want a fairly high utilization, somewhere around 0.8. So, moral of the story, have a fairly high utilization, but don't push it. So, if we want to increase utilization overall, well, how do we do that? What causes this difference between design throughput rate and actual throughput rate? Well, idle periods. So what causes idle periods? Well, a whole bunch of different things can cause idle periods. Scheduled downtime. Sometimes we have to shut things down in order to make repairs, make changes. Breakdowns. Things break. That happens. Setup and changeover. Sometimes in processes we may manufacture one item and manufacture that for a while and then switch over to manufacturing another item. Well, to do that, that requires time to change from one product to another. So setup and changeover, you can't get any done any work done during that. And then there's our old friends starving and blocking. So all of these cause this difference between our design throughput rate, in other words, how much a step in the process could get done if it wasn't being blocked or starved by anything, and our actual throughput rate. So anything that reduces these idle periods, that's going to increase our cycle time of the activity and hopefully increase the utilization. That's the ultimate goal. Remember, we want a high utilization. We don't want one, but we do want a fairly high utilization. So, the goal is to reduce these idle periods so that while people are working, they're productive, they're getting stuff done. Now, it's important to note one other thing here, and that is that ultimately, what we need to get done, it needs to have a purpose. It ultimately needs to get sold. It needs to generate value. Doing work for the sake of doing work doesn't help us. That's not playing to win the game here. But like I said, we do want to get work done that hopefully produces value, creates value that the customer is willing to buy. That's the ultimate goal here. So to do that, we reduce these idle periods, we reduce downtime and starving, and by doing this, by having work done that actually goes toward this goal of getting value to the customer, well, at this point, we really start improving our process. So, as stated, we do want a fairly high utilization, but we don't want utilization at 100%. Reason why is because actual utilization at 100%, it causes problems, because when you have any variation in a process and you have utilization at 100%, suddenly it takes an infinite amount of time, and I'm not going to go into the math details here, but it takes that long for an item to get through the process. So utilization is kind of like a campfire. You want to be closer to the heat, but you don't want to get burned. So, again, when it comes to this utilization, we want a high utilization, but we don't want it so high that we end up causing this issue where we have these moments of blocking and starving that end up effectively gumming up our system, if you will. Now, I've mentioned several rules over the course of these lectures. The first, of course, being Little's Law, this relationship between throughput rate, flow time, and inventory. I've also mentioned that you're only as fast as your slowest step. In other words, whichever step in the process has the smallest throughput rate, that's going to limit the throughput rate for your entire process. Well, sort of. You see, there's a couple of other things that we need to look at when it comes to the process. Specifically, we have to be sure that when we are comparing these steps in the process to see which one has the smallest throughput rate, we have to be sure that we're comparing the same things. You see, when we look at these steps in the process, we have to know that what we're comparing, by comparing one step in the process with another step in the process, that we're actually looking at the same things. And this can be a little tricky. You see, sometimes, the best way to put it is that usually when we calculate a throughput rate using Little's Law, we find the product that goes through that step per unit time. That's the throughput rate the design throughput rate that you usually find. However, sometimes that's not the same thing for each step, as we see. So, what we have to do when we see which of these steps has the smallest throughput rate is we have to put them in the same units. One thing that you'll find when it comes to the real world is that numbers are almost never just numbers. There's usually some dimensional component to it. So in this case, we have to make sure that that dimensional component matches for each step. In other words, we have to be sure that we're comparing apples to apples when we see which step has the smallest throughput rate. For instance, suppose we have this process here. First, we manufacture tires, and we're able to manufacture 4 tires a minute. And then those tires go into manufacturing a car. And the process to manufacture the car can produce cars at 2 cars a minute. So, which of these is the bottleneck? Well, in this case, if you just look at the numbers and just take the numbers as is, well, you'd think that the manufactured car step would, because the 2 is smaller than 4, right? Well, not in this case. How many tires go into each car? Well, if we assume 4 tires on a car, then if we're able to make 4 tires a minute, then that means 1 car a minute. So, we have to make this conversion. We have to change tires to cars, the manufactured tire step, from tires per minute to cars per minute, so that we can compare it to the manufactured car step. And when we do that, we see that the manufactured tire step has a smaller throughput rate. In this case, only 1 car per minute. So in this case, because the manufactured tire step has a smaller throughput rate than the manufactured car step, when we actually are comparing the same things, when we're comparing apples to apples, we see that the manufactured tire step is our bottleneck in this case. Now, suppose we have this example here, where we have a process where we manufacture a car and we're able to manufacture 0.5 cars a minute. And then, well, some of the cars we sell are customized. Not all of them, but some of them. So 60% of the cars we sell have some customization. And the customized car step we can complete at 0.35 cars a minute. And then, no matter what, we deliver the car and we're able to deliver 0.6 cars a minute. So we have 3 steps. Each step has a throughput rate. So which of these is the bottleneck? Well, we have to be very careful in a case like this. You see, if we had just looked at this at face value, well, we'd see that, okay, it must be customized car step because it only needs to produce 0.35 cars a minute. Well, that said, only 60% of the cars actually go through the customized car step. Now, keep in mind, when you calculate the throughput rate at each step, you're basically calculating the product that goes through that step per unit time. What you really are interested in is the product that the process can complete per unit time. That's the level of comparison that you want here. So, we have to adjust. We have to adjust the throughput rate for each step to compensate. So how do we do this? Well, we have to convert the throughput rate for the step to all completed cars. In other words, cars that the process in its entirety completes per unit time. Well, the customized car step can get done with 0.35 cars a minute. That's how much that step can get done. However, only 60% of the cars that the process completes goes through that step. So if we want to convert this to the cars that the process completes per unit time, well, we take that 0.35 cars per minute and divide by 0.6 cars per completed car. In other words, 0.6 cars that go through that individual step divided by cars that the entire process completes. And when we do this, we find that we have 0.583 completed cars a minute. In other words, cars that the entire process completes per minute. Well, from here, now we are able to compare apples to apples. We're comparing the same things because, well, every car goes through the manufacture car step. Every car goes through the deliver car step. And now, by making this conversion, well, we see how much the customized car step is able to get done in terms of cars the entire process completes per unit time. And we see that of these 3, that the manufactured car step has the smallest throughput rate at 0.5 completed cars a minute. So, moral of the story here, you have to be sure you're comparing the same things. You have to be sure you're comparing apples to apples. Numbers are almost never just numbers. There's usually some sort of dimensional component to them. And you have to take that dimensional component into account when you're looking at the steps in the process and looking at the process as a whole. So, make sure you convert the units as needed so that you are looking at the same things to see which step in the process has the smallest throughput rate, which step in the process is your bottleneck. Okay, thank you and be well.